Welcome to another video on HEC physics. In this video, I'm going to explain the DC circuits part of this electricity and electromagnetism standard in level 2 physics. Now, the main focus of DC circuits in year 12 is analyzing complex circuits. So what you need to do is basically you have to analyze complex circuits. And as part of your analysis, what you might have to do is basically you might have to calculate current through different components in the included in the circuit. You might have to calculate what is the voltage across a component in the circuit. You might also need to calculate the resistance of a component, or maybe find out the power of a component, or how much power is used by the entire circuit. So you might have to calculate these quantities, or you might have to explain how these quantities will change if you make some changes into the circuit. So these are the main things that you have to do as part of the analysis. So let's quickly look at the meaning of these quantities, because if you understand this well, then you will be able to analyze it or calculate it for the circuits as well. So quickly, a recap of these key quantities. Current. So what's current? Current is denoted by the symbol I. Its SI unit is amps. And what is it? It's actually the rate of flow of charge. Or in another way of describing it is basically the amount of charge measured in coulombs passing through a component every second. So that's how we define current. It's basically how much charge in coulombs is passing through any component every second. That's how we define current. And because of this, current can be calculated using this formula. Current I is equals to Q over T, where Q is the amount of charge in coulombs, and T is, of course, the time, but make sure that it's in seconds. And I is the current in amps. So this is current in amps. Okay. So that's how current is defined. Now, next, let's look at the second quantity that could be part of your analysis, which is voltage. You might have learned about these quantities in year 11, but just a quick recap. Voltage symbol is V, measured in units of volts, or also used, the symbol used for volts is V. And this is defined as a difference. It's always measured as a difference in electrostatic potential energy between 2 points in a circuit. So it's always measured as a difference, and it's a difference in electrostatic potential energy between any 2 points, and it's actually the energy difference per coulomb of charge. And because it's measured as a difference in potential energy, so sometimes we also call it as potential. Sometimes it's also referred to as potential difference, or PD, which is just another name for voltage. And because of this reason, the voltage can be calculated using this formula. V is equals to the energy difference per coulomb of charge. So this delta EP over here is the energy difference. It's electrostatic potential energy we're talking about over here. It's measured in joules. And this Q is the amount of charge measured in coulombs. And this is, of course, our voltage measured in volts. So that's the second quantity that we need to know about. And then the third quantity is resistance. So let's look at resistance, and symbol is capital R. You might already know unit is ohms. And it's basically a measure of opposition to the current. So this quantity tells us that how much the current will be opposed by that component in the circuit. So that's current, voltage, and resistance. And next thing we have in the list is power. So power, P, unit is watts or W. And this one here is the energy used, or I can say rate of energy change every second. So let's call it rate of energy change. So it could be energy used every second or energy provided every second. So that's what power is. And that's why power is defined as rate of energy change every second. So over here, delta E is energy change, which is in joules. And this time here is in seconds. And this is our power measured in watts. Okay. But for circuits, there's another formula that we often, this is the more general formula for power. So this formula you can use for any kind of application of energy and time. It could be in mechanical energy, it could be thermal energy, anywhere you can use this formula. But for circuits, there's another formula that is particularly used in circuits to calculate power, and that is P power is equals to current, which is the amount of charges passing through it every second, times the voltage, which is the energy difference for each coulomb of charge. So this is the formula that is quite handy when calculating power for different components in a circuit. You will get both formulas, and depending on the situation, you might have to use one or the other. Okay, so these are all the key concepts that we might be using in our analysis of circuits. There's one more formula that we are going to use quite a lot in circuit analysis, which you might be familiar with. It's Ohm's law. And this gives us the relationship between voltage, current, and resistance. And we know it's V is equals to IR. So voltage is equals to current multiplied by resistance. And as required, you can rearrange this formula for the current. Then it will be V over R, because you move this R to the other side. Or you can rearrange it for the resistance. If you want to calculate the resistance, then you need to know the voltage and the current through that component. Next, I'm going to talk about the circuit components. Okay, so what are the common circuit components? You will probably use a power supply or a cell like this, where you might know that the long side is the positive terminal and this is the negative terminal. And remember, the positive terminal is always at a higher voltage compared to the negative terminal. So this is a cell. Then if you put multiple of those cells, connect them one after another, that's like a battery. So if each cell is 2 volts, and if you connect them like this, then you get 6 volts out of it. Then next is, of course, the straight lines, which represents wires in the circuit diagram. Next common component is resistors. So these are components that provide a specific amount of resistance opposition to the current. So these are the resistors drawn as rectangular boxes. You can also see variable resistor, where you can adjust the amount of resistance it will provide to the circuit. So this is with arrow, it's showing that you can vary it, you can change the value of the resistance of that component. Next common one is light bulbs, which are drawn as circles with a cross in the circuit diagram. And then you can have other components. For example, you can have a laptop or any other thing like a speaker or anything. But the key aspect of that component is the resistance. So all you have to do is consider the resistance it provides to the circuit. Doesn't matter which component it is. The only thing that we need to worry about is how much resistance it will provide to the current. That's it. And I think we will also see voltmeters, which are used to measure voltages, and it's always connected in parallel to a component to measure the voltage across that component. And the next thing is ammeter, which is used to measure the current in the circuit, and ammeters are always connected in series. Okay, so next I'm going to talk about circuit connections. So when we are connecting these components to make circuits, we can connect it in series. So it could be a series connection, or we can connect them in parallel. So we can have a parallel connection. So let me quickly explain the difference between these two types of connection. So in series, we connect two components, or we connect all the components in a single branch. So for example, I can have a resistor connected to a light bulb, and as you can see, they are on a single branch. So this type of connection is known as series connection. So we have a single branch. Both components in this example are in a single branch, and it means that there is only one path for current. And that's why whatever the current is, if the current is I in this branch, the current through this resistor over here and the current through the light bulb will be same. So in series connection, the current I is same for all the components. On the other hand, the voltage across the branch gets split. So voltage is split between the components. So if I have a voltage of V1 over here, and this bulb has a voltage V2 across it, then the total voltage across this entire branch will be V1 plus V2. So the entire voltage is split between these two components over here. So those are the key things you need to remember about series connection. And sorry, there's one more thing. The resistance of the components. So if the resistance of this resistor is R1 and the resistance of this light bulb is R2, then in a series connection, the total resistance is simply all the resistances added together. So it will be R1 plus R2 plus dot dot dot. If you have more resistors in that branch, then you simply have to add them all up to get the total resistance of that entire branch. Okay, next let's go to parallel connection. So in parallel connection, the components are connected in different branches. So I can have the resistor on this branch, but then I can connect the light bulb on a separate branch. So these two branches we say are in parallel connection. So over here we have multiple branches And so there are multiple paths for the current. And because there are multiple paths for the current, if the current is I over here, and that current I comes to this junction, and some of that I will go through this branch, let's call that I1, and that some of it will go through this branch over here. And if I call that I2, then the current, the total current coming to that junction will be equals to I1 plus I2. So over here, basically current splits amongst the branches, and they might not always split equally. So depending on the resistance of the branches, it might split in a different way. So if a branch has higher resistance, you will get less current in that branch. On the other hand, the branches with less resistance will get more current. So the current might not split equally between the branches. The voltage, on the other hand, is same across each branch. So the voltage across each branch is same. The voltage over here between these 2 points will always be same, doesn't matter which branch you are in. And then the total resistance for a parallel connection like this is less than the individual resistances. So if I have resistance R1 over here on this branch and the resistance of the light bulb is R2, then because the current now has multiple paths to flow through, the overall resistance of the current is going to be less now. And the way to calculate the total resistance is using this relationship over here. This time we use the inverse relationship. 1 over the total resistance is equals to 1 over R1 plus 1 over R2 plus, if you have more branches, you just keep adding the resistance of each branch like that. So this is the formula that we use to calculate the total resistance of resistors connected in parallel. And from here, if you want to find out the total resistance, then what you need to do is take this formula over here, and then finally you have to inverse it to get the total resistance. So you use this formula over here that does not give you the total resistance. To get the total resistance, you have to inverse the right hand side, because then only you get R total. So this is the formula you will get in your formula sheet, and then also this formula will be in your formula sheet. So these were the key concepts you need to learn for circuits, and I hope you now have a better understanding of these key concepts. And in the next video, I'm going to show you how to analyze, or basically how to use these concepts to analyze circuits.